Corrosion. What is corrosion? Corrosion, better known as rusting, is the oxidation of a metal to a metal oxide or sulfide. Certain metals like iron or copper are susceptible to corrosion, while other metals such as gold or platinum are not. There are a few aspects when it comes to corrosion. First off, both oxygen gas and water must be present. Second, an object can rust in different places. Thirdly, rusting happens faster in acidic or salt solutions. Fourth, rusting happens faster in contact with a less active metal such as copper and slower in contact with a more active metal such as zinc. With that being said, what can help prevent rusting from occurring to a certain metal? One method that is used is galvanization. In this diagram, a copper pipe is galvanized with a coating of zinc, which is a more active metal than copper. With this protective zinc coating, the copper pipe is less susceptible to rusting than it was before standing alone.
New York City's 100-year-old Mass Transit Authority ranks corrosion as its #1 maintenance issue. But according to the American Society of Civil Engineers, we have far bigger corrosion problems to worry about.
The worst areas with a grade of D- are drinking water, wastewater. The Environmental Protection Agency estimates that nearly $1 trillion is needed in critical drinking water and wastewater investments over the next 20 years.
The very nature of wastewater is corrosive. It breaks down, and that increases the acid content in wastewater. What that means is it essentially eats away at the pipe, weakening it. It becomes much more subject to leaks and structural breakdown, which is sewer pipe collapsing.
Collapsed sewer pipes mean spills, and spills mean fines from the Environmental Protection Agency. Detroit, Atlanta, and Washington, D.C. have seen their fair share. But the worst offender is San Diego, with $6.2 million in EPA penalties between 2005 and 2008.
Corrosion is a very recurring theme in our lives today. Corrosion happens everywhere. In fact, corrosion takes place in everyday commonly used fluids that we either drink or use with our food, of which continuous use can be harmful to our teeth over time. In this experiment, we will be testing the corrosiveness of 3 fluids: vinegar, which has acetic acid, apple juice, which has malic and citric acid, and Coca-Cola, which has phosphoric acid. To test the corrosiveness of each of these fluids, we will take 3 completely dirty pennies and fully submerge them in each of the fluids. After a 12-hour period, we will take out the pennies, and however much of the dirt is cleaned off the pennies should give us an idea of how corrosive that fluid is. Now, to compare our results, we will take 2 controls: 1 shiny penny and 1 dirty penny. By using this, we should get a clear idea of which one of these fluids is the most corrosive. Let's commence the experiment. Now again, we have distilled vinegar, which is acetic acid, apple juice, which is malic and citric acid, and regular sugar Coca-Cola, which has your regular amount of phosphoric acid that you can find in any everyday Coca-Cola bottle. Now you will take each coin and fully submerge them into the fluid. And now we wait for 12 hours. This is an observation. Now in the Coca-Cola, you can see it is actually fizzing. That is because the acid and the carbonated water that is consist in the Coca-Cola is reacting with the penny. Now in the apple juice, you can actually see a few bubbles lying on the penny, which seem to have occurred when we had originally dropped the penny into the apple juice. And for the vinegar, the penny is just sitting there. So here are the coins, 12 hours later, after they have been lightly rinsed in cold water and dried. As you can see, the vinegar is the most clean, and when you compare it to the shining control, they are very similar, only that the vinegar coin has been put in use more than the shining control had. Now in the Coca-Cola, there is still a good amount of dirt on there, but a good amount of dirt has also been cleaned. Compared to both control, it is shinier than dirty control and not as similar to the shiny control. If you look at the apple juice, it has been cleaned the least and looks most similar to the dirty control, which means that the acids in the apple juice must be weaker. So as you can see from this experiment, vinegar with the acetic acid, it was the most corrosive. Then Coca-Cola with the phosphoric acid was the second most corrosive. And then malic and citric acid in the apple juice was the least corrosive. From this, we can conclude that the continuous use of both fluids can be very harmful to our teeth over time, and also shows that corrosion does in fact happen everywhere.
Corrosion presents itself as an issue affecting contemporary society. The negative impact can be measured across the country's economy, its structural stability, and environmental risk. An example of a mutagenic and carcinogenic substance that pollutes the environment is hexavalent chromium, which is used in chromium plating. This is a simple experimental demonstration that shows iron metal reacting with an acidified solution containing chromium-6. In part A, shows the experimental setup, where acidic aqueous chromium-6 is filtered through iron fillings. In part B, it shows that the resulting filtered solution is formed by soluble chromium-3 and iron-3. In part C, it shows that after changing the solution's pH, you get both treated H2O, which is now chromium-6 free, and in the bottom, you have chromium-3 and iron-2 insoluble hydroxides precipitate. This experiment shows a way in which we can lessen the concentration of toxins to a level where the water can be safely reused or discharged as wastewater. This is only a valid mechanism if it occurs during a reasonable period of time. This quick experiment allows the kinetics of the reaction to be assessed, and the reaction is found to be quick and complete, and makes it practical. From the experiment, we can get the problem. In water polluted with chromium-6, the following reaction may occur at 298 Kelvin. We have 7 hydrogen plus aqueous plus 3 iron 2 plus aqueous plus chromic acid goes to 3 iron 3 plus aqueous plus chromium 3 plus aqueous plus 4 waters. The half-cell potential of iron 3 plus is 0.77 volts, and that for chromium 3 plus is 1.38 volts. Calculate K and delta G of this reaction, determine spontaneity. In step 1, we write the half-cell reactions, calculate E reaction. These are the half reactions, and we get 1.38 volts minus 0.77 volts equals 0.61 volts. In step 2, we calculate K. We can use the Nernst equation because the temperature of the reaction is 298 K. We rearrange it and get K equals 10 to the power of 0.61 times 3 divided by 0.0592, which gives us K equals 10 to the 31st. Step 3, we calculate delta G and determine spontaneity. Delta G equals negative NF times delta E cell. N is the moles of electrons transferred, F is Faraday's constant, and we convert that to kilojoules for our problem. Delta G is negative 3 times 9.65 times 10 to the 4th joules divided by 1,000 times 0.61. That gives negative 108 kilojoules per mole. Our delta G is less than 0, making this reaction spontaneous.